So let's start. I hope I'm audible. So, so good evening, everyone. This is the interactive session for Week 8 assignment for the NPTEL course Air Pollution and Control. I'm Archita. I am a PMRF scholar at ISA Kolkata, and before we start this week's lecture, if you have gone through the lecture series for Week 8, you would know that the first lecture is about a case study of indoor air pollution. It's in the nursery schools in UAE, and then thereafter there are four different global phenomena that have been discussed, like ozone depletion, global warming, climate change, and acid rain. So in this interactive session we have questions regarding the same, and let's start. If you have any questions in between, you can ask. Okay. So, in the case study part, or in the first lecture of this week, there is a discussion about buildings and material and everything. And the one of the thing that is there, or the term that's there, is the building breakout. So, what do we understand by this term, building breakout? Is that sometimes the heat inside the indoor environment is so much that like, if, or for example, if you have a lot of VOCs in in an air environment, and you have to remove those VOCs. So what you can do is that you can have these heating systems. In India, it's not very prevalent in houses. It's there in the industries or companies. But these heating system, what they do is that they increase the temperature inside the room, which helps in removal of these VOCs, and that phenomena is known as building breakout. So that is a term there which is used. Another is that okay, so we know that World Health Organization have defined certain threshold limit for different pollutant that are there in the atmosphere. For example, CO2, methane, VOCs, etc. And CO2 being the most prevalent pollutant out there, there is a threshold limit that is being designed by WHO, and that limit is 920 ppm. So if in the atmosphere, or especially in the indoor environment, if we see that the concentration of CO2 increases beyond 920 ppm, then we can consider that environment as polluted. So and now, if you have gone through the case study, you would have seen one important thing which is which was shown in the study, or I believe that it's the major point of the study, is that if you there are four plots in these studies for each CO2, TSP, formaldehyde, and VOC. Now, the scene with CO2 and TSP is that their concentration was lowest during the afternoon, and their concentration is high during the day and night time. So, this is for CO2, this is for TSP. On the axis is the time. So, it's morning, then it's day, and then this is night. But for the formaldehyde and the VOCs, the concentration was actually highest during the daytime. Okay, no. The concentration is highest during the night time and less during the daytime. Now, this shows that for these two pollutant, okay, the inflow is can also be from the outside, because generally this is the pattern of particulate matter or CO2 that we see outside, that during the daytime, because the ventilation is so much, there is lot of circulation, okay, and because of the circulation, the concentration during the afternoon hours is very less. This is the same pattern that we see in the outdoor, and we are seeing the same pattern in the indoor environment. And because the concentration or the oxidant are higher during the day and night time, their concentration is same. Okay, so we because they are representing a phenomena which is similar to what we see outside, we can say that the CO2 and TSP can be coming from the outdoor as well. On the other hand, formaldehyde and VOCs are generally the indoor pollutant. Okay, they come from paint. They come from the material that is used to make buildings. So what happen is that during day, there are a lot of ventilation in the indoor environment, in the nursery. The example is nursery. So in the indoor environment, there is a lot of ventilation during the daytime, so their concentration is not that much. But during the night, the school is locked down, the everything is shut, and so their concentration in the indoor environment increases towards the night. So for these two pollutant, we can say that their source is only indoors, their source is only present inside the building. So the building materials themselves are the reason of high concentration of formaldehyde and VOCs um, in the indoor environment. Okay, so that is the major takeaway from that nursery study, which was a case study which was there, that the contribution for CO2 and TSP can be from outside because they show the similar diurnal pattern. Diurnal means day and night pattern. Um, and but for the formaldehyde and VOCs, the pattern is very different, which shows that their source is majorly indoor only. And that is the question here, that what is the difference between their diurnal pattern? The sources of the CO2 and TSP can be from the outside, but for formaldehyde and VOC, the contribution is from indoor only. Okay, so that is about the case study, which is the first lecture of the week. Now, then the second lecture is about the ozone pollution. If we know ozone, we know that ozone is there are two ways where the ozone can be formed in the atmosphere. One of them is stratosphere, where ozone is formed, and second place where ozone is formed is troposphere. Now, the difference between the two is that in the stratosphere, it's a good thing, but in the troposphere, it's a pollutant, it's a secondary pollutant, and it's bad. And that makes the same entity as good or bad in different environment or different layers. So now the stratosphere in ozone has a purpose, and that purpose is that it helps in capturing the UV radiations, right? But there are three different types of UV. So UVA, B, and C. Now it does not capture all of it. It captures C completely and B partially. And the only UV ray that reaches the earth is UVA, which is less harmful. Okay. Now, if someone asks the wavelength for UVB is 280 to 315 nanometer, and for UVA it's 315 to 400 nanometer, which is yeah. Oh, okay, okay. So, as I said, in stratosphere, the ozone captures all the UVC and captures UVB partially. Now they have a wavelength range. So for UVB, the wavelength is from 280 nanometer to 315 nanometer. And for UVA, the wavelength is 315 to 400 nanometer. Now, why this is important is because when you see the reaction of formation of ozone here in troposphere and in stratosphere, these wavelengths are important because generally the reaction takes place around 315 or 320 nanometer, and the breakdown of ozone takes place around 280 nanometer, I think. So these UVA and UVB are the rays which help in the breakdown of ozone as well. So that's the question, that in stratosphere the ozone only protect us from UV C and partially UVB. Okay. Now it's a good thing in yeah. हाँ. नहीं, UVA completely reaches the earth surface. Troposphere तक आराम से UVA आती है. Hmm. Then comes the troposphere part. So the same thing which is good in stratosphere is very harmful in troposphere, because in troposphere it is a secondary pollutant, and it leads to a lot of atmospheric reaction that are going on. Okay, and it's like a what I would say, that it it act as an oxidant, and it, or sort of in a chemistry term, it act as a catalyst in lot of reaction that takes place in the atmosphere, right? So in the troposphere, how ozone is formed, you have NOx coming from the vehicle or fossil fuel emission, and you have VOCs which can come from the plant as well as from the fossil fuel, and these two on the reaction leads to these radicals which later form the ozone. So this reaction is shown here. So you have these. This is hydrocarbon, VOCs, carbon monoxide. These are emitted. CO2 is, everything is like these emissions are going on. And then there is oxygen as well in the troposphere. Now these reactions lead to formation of OH. OH is one of the major oxidant in the atmosphere, and even though it has a very small lifetime, the production of OH is so much in the atmosphere that in spite of small lifetime, it can lead to lot of multiple reactions in the atmosphere, and it's a major and can act as a major pollutant. And this HO2 is same. It is just what you it's a, what do you say? Okay, there are some reservoir molecules. Reservoir molecules are made when uh, the particles react, but they make a like this OH reacts with let's say hydrogen in the atmosphere or water vapor in the atmosphere and can gives this HO2. Now this HO2 can act as a reservoir molecule and can go undergo reaction or can choose not to go ahead with the reaction. Now, these oxidant, and NO2 is another oxidant, but the problem is NO2 is majorly present during the night time, and OH is a daytime pollutant or oxidant. So that is why the if you ever see the ozone plot, that if you see the if it's 0 in the morning and if it's 23 like 11 in the night, the ozone is somewhere here. So the ozone production is highest during the afternoon hours. The NO2 production is highest during the late night, and the OH is highest during the morning hours. Okay, so that is why the chemistry of OH and NO2 is important to understand that how ozone will be formed. So, as I said, the formation of ozone depends on uh, the sorry. So for this, there is a particular H nu which is generally 350 near 315 nanometer, which is required. So in the atmosphere, you have wait. Um, in the atmosphere you have UVA radiations, then you have these oxidant OH in the morning, NO2 in the night, and VOCs are continuously releasing both in day and night, right? So in the morning OH will react with VOCs, in the night these NO2 will react with VOCs, and hence they both lead to the formation of this ozone, because all you need is this O radical, because oxygen is already there in the atmosphere, right? 24/7 there is oxygen in the atmosphere. All you need is this O radical, and if any reaction makes this O radical, it can lead to this tropospheric ozone formation. Okay, so okay, so that is why it act as a pollutant also, because this O3 can further react with the VOCs in the atmosphere and can lead to these what we call as brown carbon particles, or you can say further secondary pollutants. Okay, now why it is called as photochemical reaction. Okay, this question mark should not be. Why it is known as photochemical reaction is because there is a need of sunlight, okay, which is the H mu, and there is chemical because a lot of chemical reactions are taking place. Now, the same troposphere, that the ozone which is there in the stratosphere can actually be depleted or can actually break down by reaction with these atoms, which is chlorine and bromine, or you can call them halogens or halones. So, and the major source of these are CFCs, which is chlorofluorocarbon, and HFCs, which is hydrofluorocarbons. There are a lot of protocol we'll discuss it later. But generally, these CFCs were used in the because of their inert nature. They're Initially they were used in this refrigerator system, and what used to happen is that they in the prolonged time it was realized that as the usage of CFCs is increasing, the concentration of these chlorine and bromine are increased in the atmosphere, and because of like over 2 to 5 years, they actually can travel from troposphere to stratosphere. So because the atmospheric boundaries are not rigid, it's not like uh, that you like a gas cannot travel from one layer to another, right? So the chlorines and bromine gases which are released in the troposphere, after couple of years they can reach stratosphere, and in the stratosphere they can react with the ozone there, and leads to the depletion or the breakdown of ozone. So this figure was shown that so ClO is this chlorine oxide, let's say, and what happen in the stratosphere generally is that there is oxygen there, and initially the oxygen will break down in the presence of UV, and this oxygen will give this oxygen radicals or atoms, you can say. Um, these atoms will react with oxygen further and give this ozone. Now what is happening is that this ClO is not letting it first is not letting it react with the oxygen. That's one. Another thing is that if it reacts, let's say the oxygen in the presence of sunlight gives two oxygen atom. Now ideally these oxygen atoms should react with the oxygen molecule and give rise to the ozone. But what they will do is that if there is chlorine present in the atmosphere, okay, it react with the oxygen atom and give ClO. Okay, now if it's further there, uh, and this is called as chlorine catalytic cycle, that this chlorine will react with the O, and hence sabotage the formation. Or further what happens, so in between what happens is that this ClO or the chlorine oxide will react with another oxygen molecule and make it, no, okay, not oxygen molecule, it react with further oxygen atom. So this ClO will give Cl plus O2. So what is happening is that it is not letting the formation of ozone. Whatever atoms of oxygen are forming in the atmosphere by breakdown of oxygen molecule, it is reacting with those atoms, and hence like making the reactions, like proceed the reaction. But it's not letting the formation of ozone. If there is, that is one reaction, that it is not letting the atoms to combine with the oxygen molecule. That is one pathway. Another pathway is that these molecules will react with the ozone which is already there and further form this ClO and O2. So either it will not let it react with the oxygen atom, or even if there is ozone already formed, it break down that ozone. So it does both. Okay, so it uh, either and both way it is depleting the ozone, either by directly destructing the ozone or by this chlorine catalytic cycle, which is this ClO react with the oxygen atom and gives this oxygen molecule and chlorine. Okay, so this is important. um जी, yeah. Yeah, so both thing can happen. Oxygen can like, so we have oxygen molecule which is in the sunlight giving us lot of oxygen atoms. Now these, ideally these oxygen atom has to react with the oxygen already present in the stratosphere to give small ozone, right? But chlorine can like deplete or can reduce this process two way. One is that it can react with the oxygen atom itself, or it can and form this chlorine oxide and further than this oxygen molecule, or it can react directly with the ozone. So both way it is depleting the ozone layer. Hmm. Okay. So ओजोन के साथ तो डायरेक्टली ये रिएक्शन तो समझ आ गई ना कि हाँ, दूसरा है कि पहले क्लोरीन रेडिकल था, ठीक है, फिर या क्लोरीन एटम कह लो, एंड देन देयर इज ओजोन एटम. They react and they form this ClO. This ClO will further react with another oxygen atom which is there and gives Cl plus O2. This is how it is happening. So there is a one step is missing, that this chlorine oxide is forming by reaction with the already present molecule, or or these oxygen radical. Anyone, it reacts, form ClO. This ClO further react with the atom. Generally this sign is used for the atom to show that it's a single atom. So ClO react with the oxygen atom, gives chlorine plus O2. This reaction is the second way of ozone depletion. Okay. Okay. Yeah. Anything else? uh, uh. ये एक्चुअली हमें नहीं पता होता है, बिकॉज आवर जॉब इज टू लाइक make sure that you guys understand the different lectures series, but we don't know that the exam will be in the form of MCQ or question answer or something. So that only NPTEL can. You don't have access to the like previous year questions. Okay, then it's hard for me to tell क्योंकि हमें नहीं पता होता है ये चीज़, हमें सिर्फ इंस्ट्रक्शन होती है टू like do these interactive sessions. So like if there is, मैं पूछ के, आई डोंट नो लाइक, सो हमें ऐसे बताते तो हैं नहीं ये लोग कि लाइक. हम्म. हाँ हाँ हाँ. सो नहीं 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 नहीं, लेक्चर से ही होगा, जो भी होगा लेक्चर से ही होगा, और दैट इज फॉर श्योर. एंड आई बिलीव बिकॉज आई एम गोइंग थ्रू दीज लेक्चर एज वेल, दैट इफ यू go through the lecture really well, I don't think there will be कोई like there will be any issue in like answering question. आराम से जो क्वेश्चन आएंगे आप आंसर कर पाओगे. मे बी शायद जो न्यूमेरिकल्स आएंगे वो डिफरेंट हो सकते हैं, लेकिन उनका कॉन्सेप्ट लाइक वो जो लेक्चर है उसी से आएगा. हम्म. Okay, so let's go to the next like slide. Okay. So now this question is simple, that the first time the ozone hole was discovered in Antarctic. Now the concept of ozone hole is not a hole. It's basically that in certain, so it's a layer of gas around the earth, and in certain places the gas is thin. The thickness of gas reduces over time, because there are like, because in certain areas the depletion or the this chlorine reaction is more compared to other region, and hence they form like a thinning of ozone is called as ozone hole basically. Now how they saw is that they people have studied the concentration of ClO and ozone, and they have seen that near the 70-72 latitude, the there is an increase in the ClO concentration and there is a significant decrease in the ozone. and hence we can say that with enhancement in chlorine oxide, there is decrease in the ozone or depletion in ozone. So, and based on this, they identified or they discovered that there is like the reason of thinning of ozone in the Antarctic. Um, Now, there are few protocols or the international treaties that takes place in the world to make sure that the to the concept of international treaties is that the pollutants that are there in the atmosphere, to limit them or to make boundaries for them, so that there will be at least the things which are already present in the atmosphere, things which are naturally there protecting the atmosphere, they should not be harmed. So one of those treaty is Montreal Protocol. It's, I think, in 1987. ODS is ozone depleting substances. Yes. So, what according to Montreal Protocol, as we have seen that the source of these CLO is chlorofluorocarbons, as well as these hydrofluorocarbons and halogens are there. And the thing is that there is a very beautiful chart in the lecture. If you see that they have all of these. Pollutants are given, ODS are given, and their ozone depleting power or efficiency, and their global warming potential, which is how much they can harm or they can warm the environment, is there. And you can see that they are both. They are so the major difference between CFC is that CFC is the first fluorocarbons which were like devised or like invented, which are inert and help in the refrigeration and everything, and they have really high these ozone depleting potential, and also very high global warming potential. Now, but later the alternative for CFCs was hydrofluorocarbon, and because what they did is in hydrofluoro they don't have chlorine, so they thought that okay, it will not do any ozone pollution or ozone depletion. So for these hydrofluorocarbon, the ODP is low. Okay, they don't have a lot of ozone depleting potential, but they also have almost equivalent global warming potential as chlorofluorocarbon. So the thing was that even though to reduce chlorine, they devised another fluorocarbons in the system, but they could not come up with the solution of this global warming, that however good a substance or inert a substance is, it is still harmful for the environment in general, even if it's not depleting the ozone. And in that sense, the Montreal Protocol come into play. So what Montreal Protocol is that it devised or it give time limit to the developing and developed country, that by this time you have to phase out these CFCs and HFCs, so that we can have we can stop these ozone depletion. And if you read like now about ozone layer, yeah, ozone hole, you see that this Antarctic hole is almost like filled. There is not much. And now that there is another thing is that in the Arctic, in somewhere near the North Pole also, there is thinning of ozone happening. So the chlorine is not only coming from these CFCs and HFC, there is still sources of chlorine currently present in the atmosphere because they have huge lifetime. So if I am using HFC today, which is 2023, even after 5 years, these HFCs will be there, halons will be there, and they can still deplete the ozone. And the important thing about pollutant is that they can travel. Okay, so if you have the most important thing about pollutant is that the longer the lifetime, the farthest it can travel. Huh. हाँ, अगर हम, so if I am releasing, if I am doing HFC pollution today, it is not affecting today. It will affect 5 years or 3 years from now. So because lifetime is generally a very effective measure of how severe a pollutant is, because if a pollutant has a very short lifetime and its production is also low, we know that, let's say, a pollutant has a lifetime of week. If I am producing it today and I stop it today, then within a week, everything that is there, like every bit of that pollutant in the atmosphere, will come down, will fall in the form of wet deposition or dry deposition, and there will be no sign of it after a week. But if a pollutant has a longer lifetime, it can stay in the atmosphere for a couple of years, then it can travel also, because they move with the air, right? So if I am making, yeah, if I am polluting here in Delhi, then that pollutant can travel to, let's say, Haryana, to Punjab, or to UP, to Bihar. Even we have seen pollutants coming to West Bengal from Delhi. So they can travel that far, which is about 1500 kilometers between Delhi and West Bengal, and they can travel simply just because they have longer lifetime, and they can. So if I am making pollution here, it is affecting somewhere sitting in Kolkata, and it's as simple as that. That is why we have to, especially the pollutant which has longer lifetime, we have to stop their production, and that is when the Montreal Protocol comes into play, that it gives deadline to the countries that, okay, by, let's say, 5 years from now, stop CFCs, 10 years from now, stop HFCs, and like that, so that after couple of years, the effect of these fluorocarbons would be reduced. Okay. Uh, Now the third lecture is about greenhouse effect. Now, what is greenhouse effect? It is, so we know that there are greenhouse gases, right? So greenhouse gases are these different molecules, gaseous molecules present in the atmosphere, and what they do is that we know, and it's a like, if you know that if this is Earth, the incoming radiation is UV, right? It's a short wave radiation, because UV is what, 280 to 400, which is coming, and then another radiation which is coming is visible, right? And visible is 400 to 700, another short wave radiation. Now, once this short wave radiation comes, the Earth, something will be absorbed, and whatever is left will be reflected back. Okay. And this reflected radiation is not short wave, it is in the form of infrared. And this has a higher wavelength. So, that is why, okay. So, what they does is that you can consider greenhouse gases as like a layer of gases around the earth, and when the infrared rays are going back, they block these infrared radiations, and they, so if what they does is that they absorb the infrared radiation, and whenever something absorb, what it does, absorb means that you are taking energy, and taking energy means that you are warming, you are heating up the atmosphere. And that is what happened, that these greenhouse gases takes the long wave radiation, which is infrared, and because they take the radiation and become warm, and if every gas or every greenhouse gas is warming or blocking the infrared from going outside, what it does is that overall temperature of earth will increase. So that is what happened, and that is the greenhouse gas effect. Now, if we have these gases in order means that, let's say, if we require CO2 in the concentration of 280 ppm, which was its concentration in 18th century. Now that is still okay, that okay, CO2 concentration is within limit. It is a, like, whatever is, it is blocking from going outside, it helps in maintaining an optimum temperature. Now the problems start when the concentration of these greenhouse gases is increasing. So, for example, the present concentration is of CO2 is 410 ppm, which was about 280 ppm in 18th century. In 2020, or it is 410 ppm, which is about 100 ppm more. So, because their concentration is increasing, it is making this, you know. Everywhere the concept of mass balance is maintained, that uh, if we have, let's say, 10 different gases in the atmosphere which act as greenhouse gases, those gases will take up this much energy and is making sure that the optimum temperature of earth is maintained. Now if the mass balance, like if the balance differs or balance changes, then, or let's say CO2 concentration is very high, methane is very high, ozone is very high. Now they are blocking lot of infrared, and the more infrared they block, the temperature increases even more. So if the optimum surface temperature of earth is, let's say, um, 30 degree or 35 degree Celsius, now it is 40-45 degree Celsius, because these gases are not letting it go, like it's not allowing the infrared radiation to go away, and it's blocking it. So the more greenhouse gases there in the atmosphere, the more surface temperature, earth surface temperature will increase, and hence it becomes like a what you call, like a fireball over time. If this thing keeps on increasing, the earth's temperature would go 50 or something, which we don't want, but you cannot do anything about certain. It's okay. Yeah, you have any questions? हाँ, बोलो. Yeah, please speak. Hmm. इंफ्रारेड रेज नहीं, रेज तो यूवी और विजिबल आ रही है. सो जा रही है. हाँ. हम्म. नहीं, सी, रेज जो भी, देखो, जो सनलाइट आ रहा है एब्जॉर्ब तो उसे हर चीज कर रही है, लेकिन आपका ना पोटेंशियल होता है कि कोई गैस कितना उसे एब्जॉर्ब कर सकती है, राइट. और दूसरी चीज, जो ये सारी चीजें ना, एक चीज होती है कि पहली चीज तो इनके लाइफ टाइम पे डिपेंड करते हैं कि कौन सा पॉल्यूटेंट कितना स्टे कर रहा है, या कौन सी ग्रीन हाउस गैस कितना स्टे कर रही है एटमॉस्फेयर में. दूसरा होता है कि जैसे इसमें है कि वाटर वेपर इज ऑल्सो अ ग्रीन हाउस. सो कि पहले तो इनका स्टे कि कितना लाइफ टाइम है और क्या वो कितना एब्जॉर्ब कर पाएंगे. दूसरा, हम भी एब्जॉर्ब कर रहे हैं, वी आर ऑल्सो एब्जॉर्बिंग यूवी रेज, प्लांट्स आर एब्जॉर्बिंग, लैंड इज एब्जॉर्बिंग. सो एब्जॉर्प्शन इज टेकिंग प्लेस, बट इट्स नॉट टू द एक्सटेंट कि जैसे मैं बहुत सिंपल चीज बताती हूँ. वी स्टडी समथिंग कॉल्ड ब्लैक कार्बन. सो नाउ ब्लैक कार्बन absorb in all of the wavelengths, if you see, but we generally measure it in infrared. Now, or you can say that, how would I say it? It absorb in UV, it absorb in visible also, but it absorb maximum in the infrared, and that is a particle, it's not a gas. Black carbon is a particle, it's like a flake, if you say. So gases are not necessarily that it's the gases which absorb. Other particles or other pollutant in the atmosphere can also absorb, we can absorb, plants, land can absorb. Now earth has different surfaces, right? It has land, it has ocean, it has snow, and they absorb differently. For example, snow has highest reflectivity, so if a UV ray fall on snow, it directly reflect back in the form of infrared, only tiny bit of energy will be absorbed. If it falls on land, which is greener, there is more energy is absorbed by the earth, and reflectivity will be less. Okay, so you have to understand that not only one factor is involved. It's a lot of complex chemistry out there. It's just that we are reducing it, or we are oversimplifying it so that we can understand that how greenhouse gases function. Hmm. हाँ, देर आर गैसेस अराउंड जो जो इंफ्रारेड वापस जा रही है टुवर्ड्स दी फ्रॉम द अर्थ, वो इंफ्रारेड को एब्जॉर्ब कर रही हैं। और क्योंकि इनका कॉन्सेंट्रेशन अगर ऑप्टिमम रहेगा, तो अर्थ का टेम्परेचर भी ऑप्टिमम रहेगा। कि मतलब अगर अर्थ का आइडियल टेम्परेचर 35 है, हम मानते हैं, और हमारी जो गैसेस हैं अराउंड वो उतनी है, मतलब कि वो इतना एब्जॉर्ब कर रही हैं कि हमारा अर्थ का टेम्परेचर 35 बना हुआ है, then it is a it's like the greenhouse gas effect is not prominent. It's like a good situation. लेकिन अगर ग्रीन हाउस गैसेस बढ़ रही हैं, CO2 की कॉन्सेंट्रेशन बढ़ रही है, मीथेन बढ़ रहा है, वाटर वेपर बढ़ रहे हैं, तो क्या हो रहा है कि आपकी जो अब ऑप्टिमम टेम्परेचर हो गया ना अर्थ का, वो हो गया 40। क्योंकि वो तो एब्जॉर्ब कर रही है, ग्रीन हाउस गैस एब्जॉर्ब कर रही है, ओजोन एब्जॉर्ब कर रहा है आराम से, इंफ्रारेड। और उन्हें फर्क नहीं पड़ रहा कि अर्थ का टेम्परेचर 40 हो रहा है। फर्क किसे पड़ेगा? पीपल हु आर लिविंग ऑन अर्थ। एंड दैट इज वाई वी आर कंसर्न दैट वी आर लिव ideally it should be 35, which is like, okay, it's not very cold, it's not very hot. But now what has happened is, because there are a lot of greenhouse gases, the temperature become 40. Now it is going towards this heat direction. Oh, then somehow it will become 45 after a couple of years. So then the problem starts then, that the temperature is increasing very fast, and we are being like heating up. The problem is to us. Okay. um, then so there are few greenhouse gases which are there, which are important. For example, water vapor, CO2, methane, ozone, fluorinated gases, and N2O. Now these are all greenhouse gases which contribute to the warming, and they have different potential, that they have different extent of how much they can heat up, or how much absorption of infrared they can takes place. Okay. And that depends, that is shown in this plot, which is that CO2 has about 65% contribution. Six, what is happening? So CO2, which is coming from fossil fuel in industry, contributes 65% to the greenhouse gases, and the CO2 from the land use or forestry contribute 11%. So about 76% uh, of the warming of the earth is because of CO2. Then comes the methane, and then comes nitrous oxide and fluorinated gas, which is not that much. So that is why CO2 is the major driving factor of greenhouse gas. And that is why in the next slide you will see that why we measure the global warming potential in terms of CO2, because it is the major driving greenhouse gas. Um, okay. Now one of the greenhouse gas act as a feedback process, and that is water vapor. Now what is feedback? Feedback are basically loops. It means that if I am increasing something, it leads to increment, and if I am decreasing something, it leads to decrease. So how you can define it? Let's say there are a lot of water vapor in the atmosphere. Okay. Those water vapor, what they are doing is, so high water vapor, so increment, then this water vapor is absorbing the long wave radiation and leads to warming, another increment. And this warming further, what it does is that the other greenhouse gases, which is CO2, CH4, and ozone and N2O. So this warming of the atmosphere further enhance the production of CO2, methane, and ozone, and hence it's a positive feedback loop. And this increase in the these increase in the carbon dioxide, methane, and ozone further enhances the production of water vapor. So that is what you call a feedback loop. That and it's a positive feedback loop where you have to ask anything. Yeah, going. I'm going to explain. Okay. Let's say today I have 1 kg of water vapor or 1 liter of water vapor in the atmosphere. Now, 1 liter of water vapor absorb the infrared radiation. Let's say they absorb 1 ton of infrared. It's these are everything is hypothetical. Let's say they absorb 1 ton of infrared radiation, which leads to warming. Okay. Now, this warming, what it does is that it uh, it leads to lot of reactions in the atmosphere, जिसकी वजह से क्या होगा कि जो CO2 है उसका कॉन्सेंट्रेशन बढ़ रहा है, मीथेन का प्रोडक्शन बढ़ रहा है, ओजोन का प्रोडक्शन बढ़ रहा है. अब इनका प्रोडक्शन बढ़ गया, ये क्या करेंगे और वार्मिंग करेंगे. दे फर्दर एब्जॉर्ब दी इंफ्रारेड रेडिएशन. मान लो इन लोगों ने एक टन ईच कर ली, तो अब होगी 4 टन इंफ्रारेड एब्जॉर्ब हो गई है. राइट. अब इतना वार्मिंग हो चुका है कि जो ओशन है, ओशन अगेन विल स्टार्ट इवेपोरेटिंग एंड फर्दर वाटर वेपर बन रहे हैं. ठीक है. सो सी इट लाइक दिस कि बहुत सारा CO2, मीथेन और ओजोन था, उन्होंने बहुत कुछ एब्जॉर्ब किया एंड उसकी वजह से वार्मिंग हुई. ओके. वेट, जस्ट अ सेकेंड. सी इट लाइक दिस कि let's say there is very high CO2, methane, and ozone. This leads to warming. Warming means that temperature is high. Now, if in a surface temperature is high, what will it do? It evaporate the ocean or water body. Now the water body is evaporating. What it leads? It leads to high water vapor. Okay. Now uh, this water vapor further leads to warming. Okay. Now this warming again leads to atmospheric processes which form the CO2, methane, and ozone, which further increase the temperature. Again, evaporation, again, water vapor, again, warming. So, the water vapor, if you see water vapor, it's nothing but like H2O. It can break down very easily. It has absolutely no effect on the atmosphere. But the problem why it is a greenhouse gas is that it comes with a feedback loop. So the more CO2, methane, ozone is there, the more warming there will be, the more evaporation there will be more water vapor, which further leads to warming. So it makes a loop. Yeah. Yeah. Hmm. 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 हाँ. हाँ, that is one. Now for now you understand it that way. There is another process जो यहाँ पे डिस्कस नहीं होता, which we call as cloud albedo or cloud reflectiveness. So जो water vapor cloud बनाते हैं ना, they can also absorb infrared, right? So it's the water vapor individually and it's water vapor in the form of cloud, because cloud also has reflectivity. So if there are a lot of clouds, okay. हाँ बोलो. रिया, राइट? हाँ बोलो। सी पॉजिटिव, हाँ। हाँ। हम्म। हाँ, दैट इज ओनली पॉजिटिव। कि वो क्या हो रहा है कि पॉजिटिव का मतलब क्या है? बहुत ही नॉर्मल लेमन टर्म्स में अगर मैं बताऊं, तो अगर इफ यू आर let's say you are depositing money in a bank, okay, and bank is giving you an investment, a bank is giving you a return. So now you are more tempted to invest in bank, or to like deposit money in bank. So what bank is doing is that it is giving you um, like 3% or 2% interest, which which create this scenario in your head that okay, let's deposit more money, let's deposit more money. So this is called as I think she has left. Okay. So the thing is that positive feedback loop is when an increment leads to a further increment, that an increase in one thing initiate a cycle, and when that cycle completes, it further enhances the the main thing. That is what positive means. That if I have one if I have, let's say, 1 liter of water vapor, by the end of the process, that water vapor become 2 liter. So, okay. So you have not heard Ria, right? Okay. So I'll repeat. What I want to say in positive feedback loop is that if you have if you have one thing, and over a cycle, like when that cycle completes, it that things increases, right? So I gave this example of bank, that when you deposit money in bank, you deposit because you get an interest, and it tempts you to further deposit because you are getting an interest. So similar, and that makes a positive loop, because bank is also getting benefited, you are also getting benefited. Similarly, in the cycle, in the water vapor cycle, uh, one thing leads to an increment in another thing. Okay. High CO2 or methane or anything leads to high warming. It's a positive, right? High increment means positive. um, Now warming leads to more evaporation, positive. Now more evaporation leads to more water vapor, again positive. And this more water vapor leads to more warming, so positive means, or in हाँ, इसमें इंक्रीमेंट के सेंस में। हम्म, हाँ। सो पॉजिटिव मीन्स दैट व्हेन देर इज इंक्रीमेंट। नेगेटिव मीन्स व्हेन एक चीज के बढ़ने से दूसरी चीज कम हो जाए, वो नेगेटिव होता है। अगर एक चीज के बढ़ने से दूसरी चीज बढ़ रही है, तो वो पॉजिटिव फीडबैक लूप होता है। ओके, लेट्स गो टू नेक्स्ट स्लाइड। Okay, now this is the question is, what is global warming potential? Now, global warming potential is always measured in terms of CO2 emission, and that is its definition: the ability to trap extra amount of heat relative to 1 ton of CO2. It means that, let's say, 1 ton of CO2 can trap um, zero point 0.5 ton of infrared rays. Now, with respect to this, if I have 1 ton of CH4, how much percentage of this point 0.5 it will absorb or it will trap. That is its global warming potential. That let's say it absorbs um, 0.25 tons. So it is 0.25 by zero point 0.5 ton of infrared. That is its global warming potential. It's, I am telling in a very simpler term. It has a different equation, but the gist is that how much a particular greenhouse gas will trap the heat with respect to how much a 1 ton CO2 can trap. Okay, it's always measured in terms of CO2. And that is why one term you would have seen, which is global warming potential 100, which is when the global warming potential is measured for 100 years of emission. It generally measured like that. And so that is what global warming potential is, that when how much infrared rays is trapped by a particular gas, which is CH4, ozone, water vapor, etc., which is relative to the 1 ton, relative to the amount which is trapped by 1 ton of CO2. मतलब अगर 1 टन CO2 0.5 टन इंफ्रारेड कर रहा है, तो जो मीथेन है या ओजोन है वो कितने टन इंफ्रारेड करेगी. ओके, एंड देन यू फाइंड कि वो CO2 का कितना परसेंट कर पा रहा है, यानी कि CO2 के कंपैरिजन में कितनी इफेक्टिव है कोई ग्रीन हाउस गैस, वो उसका ग्लोबल वार्मिंग पोटेंशियल होता है. ठीक है. हम्म. अच्छा, अब ये जो ग्लोबल वार्मिंग पोटेंशियल होता है, इट डिपेंड्स ऑन टू थिंग्स, and those two things are the time and the effectiveness. Okay, stay means that what is the lifetime of a gas. If a gas has a very small lifetime, then it is getting it cannot trap lot of heat, because uh, after couple of years it will be gone, right? And next is effectiveness, means how much it can trap. Okay, so for example, after CO2, methane is has a very high global warming potential. It means that CO2 तो कर रहा है, उसके बाद मीथेन बहुत ज्यादा हीट ट्रैप कर रहा है. नाउ अगर मीथेन का लाइफ टाइम विच इज आई थिंक अबाउट 12 to 13 years, सो एंड CO2 का लाइफ टाइम तो उससे भी बहुत ज्यादा होता है. सो अगर एक गैस 12 साल, मीथेन 12 साल एटमॉस्फेयर में रह रही है और वो कितना ज्यादा हीट ट्रैप कर रही है, ये दोनों चीजें डिटरमाइन करती हैं कि उसका ग्लोबल वार्मिंग पोटेंशियल कितना होगा. जो गैस का जितना छोटा लाइफ टाइम, छोटा स्टे इन द एटमॉस्फेयर, और जितना कम वो हीट ट्रैप कर पा रही है, ठीक है, वो उतनी ही कम ग्लोबल वार्मिंग कॉज करेगी, right? For example, gases like O2, NO2, or halogen, not halogen, the inert gases, argon, for example, they don't have any effectiveness, even though they are present. Okay, it's not like only CO2, methane, or ozone is present in the atmosphere. Gases like oxygen is there, nitrogen is there, but इनका ना इतना effectiveness है ही नहीं. They have a long term stay in the atmosphere, but they cannot trap heat, and that is why they don't have a high global warming potential. So इन दोनों चीजों पे global warming potential depend करता है. Now with global warming potential, another term is there, which is radiative forcing. If you would have seen that IPCC report का एक plot था in the lecture, which shows that how much a particular pollutant can absorb or can scatter. Okay, so the more it absorbs, the more it warms, the higher reflectivity or scattering it has, the more cooling it will cause. Okay, so there are in the atmosphere we have CO2, we have methane, we have ozone, we have different aerosols. Aerosols may you have aerosol like sulfate, which is a scattering aerosol, and there is aerosol like black carbon or brown carbon, which are absorbing. So generally, when the radiative forcing was discussed, we see that on the scale of cool, and this is, let's say this is warm. So CO2 is on this edge, which is, it leads to warming. Methane, again warming. Ozone, warming. Aerosol, scattering ones are cooling, and absorbing ones are warming. So what they do, warming means that the pollutant is taking the energy, keeping the energy, and hence leads to increase in temperature. Okay. And scattering means that when the light hit a particle, it does not let it enter. The light hit the particle, reflect back, or scatter in all the direction. So scattering means that light comes, it hit a particle, it goes in different direction, it does not enter the particle. And that is why the particles which scatter, they leads to more cooling of the atmosphere. And depending on different pollutant which can either absorb or scatter light, we define the term which is called as radiative forcing. Okay, so it is called as the shift in energy balance that cause the earth's average temperature to become warm or cool. So generally the overall temperature of earth changes between warming and cooling depending on the concentration of these pollutant, but it's the difference, or the radiative forcing in the shortest form you can say that the incoming radiation minus the outgoing radiation. So whatever is incoming, some of it will be absorbed, the other will be scattered, okay, or will reflect back. So if the absorbing one is high, or the incoming is high and the outgoing is low, okay, it means that the rays come, it get absorbed, so the rays which are going back are less. What will it cause? It cause warming, okay. But if the rays which are coming are less, or let's say 10 rays are coming, but because of scattering 20 rays are going back, okay, so the infrared radiation which is going back is more, and the UV visible ray which is coming is less, it leads to cooling. And that is what you call as radiative forcing, the balance between the incoming and outgoing radiation, which is determined by different pollutant, that how absorbing or scattering they are. Okay. Now next term is this AGGI, which is the annual greenhouse gas index. And what it does is that all you need to know about this is that it measure the how much warming uh, these greenhouse gases are doing. So it just measured the impact, and I think that is what is written there in the lectures also. So all you need to know is that it measure that how much climate is warmed by the greenhouse gases. Okay. Now this next, हाँ, बोलो. इसके बाद जो हाँ नेक्स्ट है वो लास्ट है क्यों. Okay. Okay, okay. um, so next is the significant contributor to the warming. So as I mentioned here, that warming is done by this, and ozone itna nahi karta, and this black carbon. So that is what their CO2, methane, and black carbon leads to warming. Acha. Next is how change in the Earth's orbit and rotation affect the climate change. This is the fourth lecture of this week, which talks about climate change. Now, the important thing here to notice that if you would have read somewhere, there are in the Earth we have these glacial and interglacial periods. Now, the difference between glacial and interglacial periods are, glacial means that the temperature was so high, everything was snow, and there are a lot of glaciers, lot of ice, all of that. Interglacials are when the temperatures are low. So, before the actual life started on the earth, there are lot of multiple periods of high temperature and low temperature. Sorry, it's the temperature is high in interglacial because it's warm, and glacial may there is low temperature. So before the life begin on the earth, there is multiple periods of high temperature and low temperature, and that is because of the earth's orbit and rotation, because we know that earth revolves around an axis, and a part of it is always like in the direction of sun, and a part will be away from sun. The part which will be away is cooler, and the part which is near is warmer. And because of this, there is, so there are, like, let's say few years, so here will be a glacial period, here will be warming or interglacial period, you can sense it like that. So this is due to change in amount of sunshine, because a certain region receive more sunlight compared to other region, and long periods of cold temperature. So even now, the places like Greenland, Finland, or like Iceland, they have very high temperature. Their cold temperature goes up to -10, -20 even. And regions like us, so the nearer you are to the equator, your temperature is more or less balanced. The further you go from the equator, your temperature is either very high or either very low. So that is why these cycles are there, which is high temperature and low temperature cycle, and that is what caused the climate change, or that is basically one of the factor of climate change. Now the climate change can have natural as well as can be from the natural as well as man-made activities. So for the natural activity, the example is the volcanic activity, the change in Earth's orbit and rotation, and then there is natural CO2 concentration. So I'll discuss this a bit. So natural CO2 means that, okay, how do we know that there during this to this, let's say there is glacial period, during 10 to 15 there is interglacial. So how do you know? We know it based on these ice cores. So scientists study, they go to the glaciers, they go to areas which I discussed like Greenland or Antarctic or somewhere, and they do these ice coring. And in the ice core, they study. So ice core generally have a habit of trapping the CO2. Okay, so they study this CO2 which is trapped in the ice cores, and they find the time. Now, how it how these glacial and interglacial period affect the CO2 concentration means that, let's say if I have a glacier here, okay, in a region, let's say this is Antarctic, and you move here, this is plain, this is let's say this is South Africa, the lower part of South Africa or South America, for example. What happen is that in Antarctic you have ice cores which has CO2 trapped. Okay, and now this is like, or you like, okay, wait, I'll explain it in a different sense. So let's say this is ice sheet. Okay, and over time, so here the concentration of ice is high, and here it's low. Now what happened is, here it's a glacial period. Just imagine that this is uh, a part which has high snow, and this is nearby region where snow is melting. So where the snow is melting, what will happen? The trapped CO2 will go out because it is there in the ice core. Okay. So when during the interglacial or the high temperature time, the CO there is melting of snow, and because of melting, the CO2 is released, and because of this release of CO2, the concentration of CO2 increases in the atmosphere. And during the glacial time, the temperature is low, there is lot of ice formation or snow formation, and the CO2 is trapped. So in a trapped CO2 case, the concentration is decreased. So the glacial and interglacial periods which has happened in the past, they actually lead to high concentration of CO2 in one place and low concentration in another. And that is why it is important to understand that how and that CO2 actually could be a driving factor to the climate, because we know that high CO2 means high greenhouse gas, high greenhouse gas effect, all of that. But the thing is, this CO2 you are not generating. This CO2 is already being trapped in the ice sheets or glaciers. The problem is that those ice sheets are melting. With melting, the CO2 is released, and this CO2 is causing the problem. So that is why it says that the changes in natural CO2. It's not the CO2 you are generating or we are generating at present. It's the CO2 which has been generated over past 100 years but was trapped in the ice. But as the ice melted in the interglacial period, this CO2 is released, and hence uh, the climate change also increase. So that is important. Now another about the man-made. Huh? So we have this method called carbon dating. So we have this from the ice core. uh, they study that they study the ice core for the carbon dating. I don't know the actual process. I know that they have like thick ice core of about meters, like meter, 2 meter, 3 meters, from regions like Iceland or Antarctic. And they undergo the process, and they uh, the CO2. So I believe what used to happen is that they melt the CO2 for each section. Okay, they take, let's say, 10 centimeter or 100 centimeter. They melt that ice core, and the CO2 which is released, they pass it through that carbon dating machine. And then the carbon dating machine can identify the type of isotope, carbon isotope there, and they do some calculation to determine what is the age of this carbon, what is the age of this carbon. And then they back calculate, okay, this ice core was, let's say, 10 years old or 100 years old. And then they calculate that, okay, so at 100 years from now, this much CO2 was there. That is how they got to know that in 18th century, there the concentration of CO2 was 280 ppm. No one can measure concentration in 18th century, right? That time we don't have these gas analyzer or anything. We got the value because of these ice core. We we ca- uh, we uh, analyze the trapped CO2 in the ice core using carbon dating, and then we come up with a number that, okay, 10 years from now, or 20 years in the past, the CO2 is this much. And this is the year, like let's say in 1920 this is a CO2 concentration, in 1800s this is a CO2 concentration. So that is how they do carbon dating. Okay. Yeah. Then that it can also come from man-made energy or man-made activities. First is simple greenhouse gases, which are there, which we are generally generating at present. And next is reflectivity and absorption of sun's energy. So it means that the different surfaces, which is land, ocean, it's basically the albedo, that how much land can absorb sun's energy, how much ocean can absorb, how much snow can absorb, and how much it can reflect. That also determine that what is the climate. So the simplest example is that snow has generally high albedo, but because of deposition of this black carbon or soot particle on snow, its albedo decreases, hence reflectivity decreases, but its absorption increases. So the pollutant that we are generated can also affect the reflectivity and absorption of different landmass in the, or different component in the biosphere. Okay, this is the last. It's about, I think, acid rain. Okay, before this one, so next is what are the future effect. So future effect can be टेम्परेचर बढ़ सकता है, प्रेसिपिटेशन पैटर्न बहुत चेंज होता है बिकॉज ऑफ क्लाइमेट चेंज, फ्रॉस्ट फ्री सीजन होता है जब ग्रो करती है कोई फसल या कोई हार क्रॉप, एंड उसका पीरियड बढ़ सकता है, देन सी लेवल बढ़ सकता है बिकॉज लॉट ऑफ आइस इज मेल्टिंग, बिकॉज जितना ज़्यादा टेम्परेचर बढ़ेगा उतना ज़्यादा जो ग्लेशियर है वो मेल्ट होंगे, और जितना ज़्यादा ग्लेशियर मेल्ट होंगे उसका पानी कहाँ जाएगा, वो पानी सी में जाएगा, तो सी लेवल बढ़ेगा. सो द मोर द मेल्टिंग ऑफ ग्लेशियर द हायर विल बी द सी लेवल. एंड दैट इज वाई वी हैव लॉट ऑफ ड्राउट्स एंड हीट वेव्स दीज डेज, कि कहीं पे बहुत ज़्यादा सूखा होता है, कहीं पे बहुत, जिसे हम लू भी कहते हैं, बहुत ज़्यादा लू हो रही होती है या हीट वेव्स हो रही होती है. ऑल ऑफ दीज इज बिकॉज ऑफ क्लाइमेट चेंज. ओके, कहीं पे बहुत ज़्यादा बरसात हो रही है, कहीं पे बिल्कुल ही ऐसा है कि लोग तरस रहे हैं कि बारिश नहीं हो रही है. फॉर एग्जाम्पल एट प्रेजेंट इफ यू सी दैट इन रीजन लाइक दिल्ली, उत्तराखंड, हिमाचल, ऑल ऑफ दीज रीजन, for for couple of hours in a day there is sunlight and then there is lot of rain, then again next day there is sunlight and there is rain. So you cannot even predict that okay, today is a sunny day or it's gonna be rain the entire day. And that is also one of the effect of climate change. And this thing which bind the different countries is the Paris Agreement. So this you need to know that Paris Agreement is an international treaty which works on the principle, or which on the um, on climate change, or how to control the climate change. Next is acid rain. So acid rain, like we call it acid rain because it has a pH which is below 7. Now the ideal pH is 4.2 to 4.4. Now there is something called normal rain or clean rain, which has a pH of 5.6. So if a rain does not have very high concentration of pollutant or the gases which we discussed, which is NO2 and SO2, then we call it clean rain. And if it has high pH, we call it acid rain. Now, the two major oxide which could be or which are the reason of high or the high pH, not high pH, the low pH of acid rain is the NO2 and SO2 oxides, and they are the reason they form this HNO3 and H2SO4, sulfuric acid and nitric acid in the uh, via wet deposition and lead to this acid rain. Next, hmm, क्या? हाँ, HNO3, अगर एक्चुअल HNO3 हो उसका पीएच तो नियर 1 होता है. H2SO4 का पीएच भी अगर आप केमिस्ट्री लैब में देखोगे तो इनका पीएच ऐसे 1 के अराउंड होता है. बट द पॉइंट इज कि एटमॉस्फेयर में क्योंकि इनकी कॉन्सेंट्रेशन कम होती है कंपेयर टू द अमाउंट ऑफ रेन यू हैव, ओके, द कॉन्सेंट्रेशन ऑफ ऑक्साइड इज वेरी लेस. सो ये क्या होते हैं, ये डाइल्यूट हो जाते हैं. तो इवन दो ये उतने एसिडिक नहीं होते, सोचो एक 1 pH का पानी ऊपर से गिर रहा है या रेन ऊपर से गिर रही है, एवरीवन वुड बी लाइक हर्ट, इवन अस कैटल्स, एवरीवन would have like marks on your body because that is like very very acidic. So but the rain or the rain droplets are so much that it dilute the effect of nitric or sulfuric acid which form, and that is why the pH is 4.2 to 4.4 instead of 1, which is their pH. Their actual pH is 1, the raw acids. So NO2 and SO2 does not have a pH. When they react with the water vapor in the atmosphere, they form the HNO3 and H2SO4, which have low pH. Yeah. So gases don't have pHs. They only, when they react and form these this, they attach this H with them, then the, because pH का जो फॉर्मूला होता है वो होता है माइनस लॉग ऑफ H, राइट. सो द मोर द H in a component, the chances is it is acidic. Okay. Now next is there are this thing which I believe you need to remember is the Acid Deposition Act. and the year is 1980. So just remember the date. एंड अनदर थिंग इज दैट जनरली हमें क्या लगता है कि एसिड रेन है मतलब वेट डिपोजिशन होगा, बट एसिड रेन कैन ऑल्सो बी फ्रॉम वाया ड्राई डिपोजिशन. एंड ड्राई डिपोजिशन के जो मेथड हैं वो ज़्यादा लिखे नहीं हुए हैं ऑन दी in the lecture, but what they suggested is that there is a network which is called Clean Air Status Network. Remember this name. And what they do is that they have, I think it's a satellite or something, I don't know about this, like lot of things about this, but it measure the, or it comment on the value of dry deposition, how much acid rain can be coming from the via dry deposition. So that is, you need to remember, because wet deposition ka, you know that okay, it react with water, it forms these HNO3 H2SO4 which come down. That is wet deposition. Okay, but for dry deposition you don't have any, they directly deposit in the form of gases. Okay, a gas which is there in the atmosphere can just settle on a surface, on your hand for example, on the surface of a metal, or on buildings like Taj Mahal or your house even. So you cannot see it, the dry deposition, until it is in the form of particle. Okay. So to measure it, it's even harder, and that is why they have this network. Okay. So you just need to remember the name. I believe. Next is the buffering capacity of soil. Now, the good thing about soil, or why soil is very important in certain region, is that soil can neutralize this acid. Okay, and it reduces the pH, or like it makes it more neutral, and that is what you call as buffering capacity of soil. That when this acid rain will fall on a soil surface, and then it is going through the soil, what it does is that soil will capture these gases, like if the soil need nitrogen, if the soil need sulfur or oxygen, it will take that from this uh, acidic rain, and will sort of neutralize and make it into just water which is going out of the, or coming out of the soil. And that is what you call it buffering. Buffer means that you are neutralizing the acidity of rainwater, and that is why soil are very important. Next is that on what this buffering capacity depends, and that is the thickness and composition. So some soil, like for example, if it's a loamy soil or like black soil or something, I don't think that is, that could do the neutralization. So you have different types of soil, right? So you need to know that which type of soil is how effective in doing the buffering. Okay, so and the composition of soil depends, that a soil has calcium carbonate, or a soil has magnesium or not. All of these factors will depend. And the type of bedrock means the, soil has layer. So the bottomest part of soil is bedrock, which has lot of boulder and like lot of bigger, um, it act like more. Yeah, hello. No, no. So, bedrock is basically, in soil there are layers which you call as A, B, C. I don't remember the exact name, but on one layer there is lot of organic matter. On another layer there is something. So, bedrock is the bottom part of soil, like from where the soil actually start. Let's say, and it has these bigger. Uh, like rocks. So have you seen that filtration system which they generally, yeah, so in that filtration system there are a lot of soil layers from the and how it changes from the thinner particle to the thicker particle. And the soil and the when the water go through that filter system, it is more or less clean. And that is what they meant by the term bedrock. It is nothing but lot of pebbles and rocks, and the type of pebble and rock which form the bedrock or the bottom part of soil, and that determine the buffering capacity of the soil. And the last is the episodic acidification, which is uh, like if for a short duration, let's say in a rainforest, there will be rainfall for not rainforest, let's say in a forest the rainfall is for, let's say, 1 hour, or let's say 30 minutes, and it's very high acidic rain. And now the effect will be short term, because for that 30 minutes, or let's say after that 30 minutes, let's say 20-30 minutes after it, so for that 1 hour there will be effect on the forest. Okay, the leaves can get affected, the soil will have high acidity and everything. But once the duration is crossed, there is no acidity. The acidity will not stay in an ecosystem. The rain comes, it enhances the pH or to acidic, and it leads to these short term stress to the plants and the soil and everything. But once the acidity once the rain is gone, or acid rain is gone, the effect itself decreases, and hence it's gone. Okay, that is episodic, that when the acidification is for a very short duration, and over time it declines, and then it completely stops until another event of acidification increase. Okay. uh, for example, the acid mine drainage is not an episodic acidification. Okay, it's a long term acidification because it's happening continuously. But an event like rainfall in a forest, or rainfall here over couple of in a polluted region, is a short term or episodic acidification. So that is it for today. Do you have any of you have questions you can ask? Otherwise we will. Huh. Good evening. Bolo. Yeah, yeah, yeah. Not standard scale. See, I in the lecture, this lecture only, I said that global warming potential they are determining in terms of one gas. Okay, they have measured that how much CO2 is causing global warming. Okay, and based on that, which is the most potent climate forcing, or the most potent greenhouse gas, based on this one gas, which is CO2, they are determining that okay, how much methane is, how much harmful methane is in comparison to CO2, or how much harmful ozone is in comparison to CO2. So that is what standard scale is, that they are devising one gas which is the major polluting or major greenhouse gas, and they are representing other uh, the potential of other greenhouse gas in terms of CO2. Okay, so let's say we say in that plot, in that figure we say that CO2 is contributing 76% of all the greenhouse effect, right? Now, global warming potential is saying that if I am considering CO2 is the major global or greenhouse gas, then I am saying that now my uh, now I am devising that okay, other gases, for example, methane is 10% as effective as CO2 in terms of greenhouse, or ozone is 2% as effective as CO2. That is what standard scale means. Okay. It's not pollutant, it's like see, heat wave means that the temperature is really high, right? Yeah, so it is not, you cannot call it as a pollutant, you can call it as a phenomena which is happening due to climate change. Okay, there are a lot of gases in the atmosphere, a lot of pollutant, and because of it the temperature is arbitrary. Okay, like for example I said, like today we have no clue that we'll have rainfall for 5 hours, then suddenly we have sunlight, and then again we have rainfall. So because the temperature is very arbitrary, that is also because of climate change. Similarly, if in certain region the pollution is so high that the temperature, uh, or like heat wave is a type of effect of climate change, that in a certain region pollution was this high that it leads to increase in temperature. That is why the wind which is blowing, okay, it is taking, it is what you get, it is capturing the temperature which is there. Okay. So high temperature, as I said, means that the energy which is earth radiating back is high, or is there is lot of absorption by the gases or pollutant in the atmosphere. Okay. So the energy which is coming from the earth is trapped by the pollutant, leads to high temperature. Now you add the component of wind. Now wind is moving, and the particles which has high temperature, or let's say these are tiny like balls which are heated, and they are moving with the wind, and that is what heat waves are. That these tiny gases or particle which are absorbing which are absorbing the infrared ray which is coming from the earth, they act as, let's say, tiny sphere. Okay, tiny heated sphere. And now when the wind is blowing, or when the high wind speed is there, what is happening is that the wind is taking these particle or pollutant with itself, and that is what heat wave is. It is taking these tiny hot spheres with itself. Yeah. Yeah. Okay. Okay. So see, any pollutant that is there in the atmosphere, they can get deposited either in the form of, either directly. Okay. So as I said, that a gas is there, it's there in the atmosphere, it comes in contact with a surface. It could be a human, it could be a cattle, it could be a building, it could be a iron rod, for example. It comes in contact with that um, that material, and it get deposited. Or there can be particles like how you would say that, let's say I burn these paper, no, and tiny black things emit, you consider that as particle, and they got deposited. That is dry, when there is no precipitation involved. Now wet deposition means that there is precipitation involved, either in the form of rain, either in the form of snow. And that is what that is where the difference lies, that in one precipitation is involved, in another no precipitation is there. Now the thing is that in acid rain, when there is precipitation involved, it means that these HNO3 H2SO form is forming in the atmosphere, is coming down as rain. You collect the rain, you measure its pH. If the pH come around 4 to 4.4, you can call it as acid rain, full stop. That is how you are done with the wet deposition part of acid rain. When it comes to dry deposition, you have no idea that like, because you cannot measure how much it is from, or like, is it coming, or has it deposited, is the gas like come, has already come in contact with the material or not, is the particle deposited or not. So that is why they have devised sort of a library. I think this castnet network which I they mentioned is sort of like a library where a lot of people have studied this dry deposition of acid rain on different material or regions, and they have made a directory that, okay, if on this surface this much deposition is there, and we measure it using some high profile instrument which they have not discussed, and then the amount is this, or the pH is this. So that is it's a very the dry deposition concept was not discussed that much, but it's a very complex concept for acid rain. Okay. So if you no one has any issue, we'll end. uh, uh, in the next class I will make sure I will do that adiabatic lapse rate thing, and the atmospheric stability part, and I will try to incorporate the week 9 lecture with it. But if I can't, then I will postpone the week 9 lecture and I'll do the adiabatic lapse rate part. Okay. Okay. So thank you for today. We are done for today. Thank you so much.